Now, what's interesting in this with the electromagnetic force, um, classically, what we've been talking about, is that the electric fields are pushing off each other. But actually, what's happening according to the standard model is that there's an actual exchange. So here's an electron, right? And this electron are both moving, and they interact with each other. They push off each other. This electron takes off this way, right? The other electron takes off this way. And what actually happens is there's an exchange of a photon. So this electron shoots a photon off like this. It hits this electron, and conservation of energy or conservation momentum, they both head off, right? It absorbs it. This electron, however, when it shoots this off, it shoots off in this direction, conservation of momentum. And so really, in the electromagnetic force, we're dealing with the exchange of a photon, which should, it's kind of sounds kind of strange, right? So again, the top electron shoots off, or shoots out a photon, and then goes to the bottom right, and then the bottom photon absorbs the photon and goes downwards. Now, Richard Feynman helped, well, he did a lot of things, but one of the neat things that he was able to do was communicate these very, very difficult ideas into ways that normal people like us could understand, right? Just people that aren't experts in particle physics. Now, these diagrams, are a little bit well, they're very helpful. They can get quite complex, and so we're just going to look at the very basics of it to look at that. Now, for the diagrams that you're going to see here, the time is going from left to right, and so you'll see that here. Now, the diagrams that I'm about to show you, the next 5, show the same thing if we look at it from the right angle. So, in other words, here, let's say you have an electron, right, and it absorbs a photon. Well, if it does that, it's kind of like a collision. These two collide together, they move off together, right? And so you've got that. Now, this one should look kind of strange because a positron absorbs a photon, right? Well, that's, if time is going from left to right, right? So here's time is going from left to right. It looks like these positrons are going against time and absorbing, right? It looks like, this photon or electron's going here, it's absorbing this and then going this way, right? Well, it's not exactly that way. So we're not really moving back in time. That was one of the things as I was working back through this. I wanted to find a good explanation of what's actually happening and why the diagrams are the way they are. So I'll give you, well, you can go ahead and pause the clip and read through this and then put the underlying things in there. And I think that'll help you understand a little bit more about these diagrams. Okay, so in this case here, an electron emits a photon, right? So this electron is going up, and as it emits a photon, right, this one shoots down like this, conservation momentum. This one, right, a photon actually materializes, right? So you have energy materializing into matter. You have an electron coming out as well as a positron. Now, if you notice here, anytime you have an antimatter, an antiparticle, their arrow is going to be pointing against time. And like we saw in that last clip, it's not really going backwards in time, but for this to be represented correctly, it's got to be going backwards. And so likewise with this, if an electron and positron collide together, they annihilate each other and a photon's produced of energy. You've got that here, the electron and the positron collide. Now, what's interesting about this is in all of these pictures, notice what happened with the arrows. This arrow is continuing like this. This arrow continues like this. This arrow, both the arrows are continuing. This one, both arrows are continuing. This one, both arrows are continuing. And then you have the photon out there. This is actually the exact same picture. If you rotated all of these and looked at them, they're all the same picture. And so back to that quote that I just showed you, this is showing that, maybe it's just the same particle, but going backwards and forward in time. And so, yeah, hopefully that helps with the intuition there. So now what we're going to take a look at is this idea of annihilation. We've already looked at two examples, the antiproton and the proton colliding, and then energy being produced. Same with this electron and the anti-electron here. So annihilation, occurs when, you have, the two annihilate and then you have something being produced. Now, in this case, this is kind of interesting. You have an electron and a positron colliding together. That becomes a photon. And then that photon becomes a particle and an antiparticle after that are produced. So afterwards, you have a new particle and an antiparticle that are going out. And so that's an important idea where you can go back and forth from energy to mass, right? Where we looked at in that earlier, earlier in nuclear, where mass and energy are interchangeable, right? So, yeah, so it's an important idea here. Now we know, and this I probably should have had earlier. What these pictures are called are interaction vertices. So interaction vertices are what these pictures are showing here. We looked earlier at electron scattering, where we had an electron push off the other one, and the medium, the exchange particle, was a photon. And that's what we call these, the exchange particles, where this electron exchanges, it sends the photon and this one absorbs it and shoots off.